In this lecture, we're going to discuss two very important theorems in number theory. The first is called Fermat's theorem, and the second is called Euler's theorem. And these theorems are actually very closely related, which is why we're doing them both in a single lecture. And actually, it's going to turn out that Fermat's theorem is a special case of Euler's theorem. So Euler's theorem is the more general one. However, Fermat's theorem came first historically, and so we're going to start with that one. It's a little bit easier to understand than Euler's theorem. So here's maybe a motivating example. So let's consider the powers of a number. So let's take the powers of 3, for example. Okay, so we have 3 squared, 3 cubed, 3 to the 4, 3 to the 5, 3 to the 6, etc. And 3 is 3 squared is 9, 3 cubed is 27, but let's only keep track of the last digit, actually. So this will be the last digit. 3 to the 4 is 81, I'll just keep the 1. 3 to the 5 is 243. We can already see the last digit is going to be a 3, just because it'll come from 1 times 81 times 3. So we just do 1 times 3 is 3. And then we'll get a 9 again, and 7, and 1, 3, 9, 7, 1. That's going to repeat. So we actually have a repeating pattern. So it's a length 4 repeating pattern. Okay. And you might have actually discovered things like this pretty early in your math education. Like maybe the first time you learned about exponents, you saw that the last digits start to repeat like this. But this leaves us with many questions, right? In particular, so I guess why do they repeat, and also why is the number 4 coming up here? It's a bit strange. Taking powers of 3. What are we doing exactly here when we're looking at the last digit? Well, we're looking at this sequence modulo 10. So this is basically modulo 10 arithmetic. Okay. But still, yeah, what does the number 4 have to do with 10? Okay. So let me go to another page here. We just looked at this sequence here. So I've got a chart, and all of the powers are appearing here, starting with the digit in the first column. So if we start with 3, we get 3. If we square it, we get 9. If we cube it, our last digit is 7. And we see the pattern repeats. But you can look at the other rows here and see that we don't always get a length 4 repeating pattern. Sometimes we get a length 1 or length 2 as well. Notice I didn't have the 0 row because that one's pretty boring. It's just all zeros. Right. So this chart is a bit maybe hard to understand what's going on here and why we're getting all these different patterns. But there's nothing special about 10. We can pick another modulus as well. And so I've done that below. Why don't we pick a prime modulus? Often things are easier to understand when we have a prime modulus. And taking any of the numbers 1 through 6, we're going to look at the sequence of powers modulo 7. So for example, 2 squared is 4, 2 cubed is 8, but that's congruent to 1 modulo 7. 8 is the same as 1 in z mod 7z. And you see, as soon as we get a 1, our pattern will repeat. Right? 2, 4, 1, 2, 4, 1. And the same happens with 3, although we have to go all the way out here before we get a 1. So it's a length 6 repeating pattern. We have a length 3 repeating pattern if we start with 4 and take the powers of 4. We also have another length 6 repeating pattern if we start with 5. We have a length 2 repeating pattern if we start with 6. 6 squared is 36, which is congruent to 1 mod 7. And you might notice something interesting in this table, which is right here. If we raise any number to the 6th, we're always going to get a 1, or we're going to get something congruent to 1, modulo 7. And we're not really seeing that up here. I mean, you could say maybe if we go further, but I mean, certainly the 5 here, we're never going to get a 1. It's pretty clear what's happening there. But this is actually exactly what Fermat observed. So if we're in the integers modulo 7, if we raise any number 1 through 6 to the 6th power, we're always going to get 1. And this happens with any prime. So if we're in the integers modulo 13, for example, well, what's the relationship between 6 and 7? 6 appears to be 1 less than 7. So in the integers modulo 13, we would, if we raise anything to the 12th power, we're going to get 1. And so in general, this is actually Fermat's observation. So, and this is called Fermat's theorem. The observation is if P is a prime. So if P is a prime, this is one of those things in number theory that only really works if you have a prime. Then for any for any integer modulo, let's say it this way. So for any non-zero element of z mod pz, okay. So we're not allowed to have a multiple 7, but or multiple p, but we can have anything else. This is going to be true. It's going to be true that if we take that element and raise it to the p minus 1 power, 1 less than the prime. So if p is 7, this is going to be 6. That's sort of the magical power. We're always going to get 1, no matter what a is, okay, as long as it's not 0. So we're always going to get 1 modulo p, or in z mod pz. And this turns out to be really, really useful. Here's an example. We're going to prove this as well, but before we even prove it, I want you to get a sense of how you might use this. So here's one way you can use it. Let's compute a huge power of a number, modulo some other number. Sort of a typical way to use Fermat's theorem. This is also called, by the way, Fermat's little theorem. Just to sort of differentiate it with the other famous Fermat's theorem, which is Fermat's last theorem. Let's compute 7 to the 2000th power. And we'll do that modulo, not modulo 10, but modulo a prime. So, well, modulo 7 will be pretty boring, I'm sure you would agree. So let's do modulo 13. Different prime. And the way we're going to do this is to take advantage of Fermat's theorem. What does Fermat's theorem tell us? So what Fermat's theorem tells us, is that if we do 7 to the 12th power, 1 less than the 13, that's always going to be 1. It doesn't matter if it's 7. It could have been 6 or 5 or 4 or anything else, as long as it's not 13, something congruent to 0 modulo 13. But this is what Fermat tells us. And so the powers are going to sort of loop back on themselves. We're going to get 1 every 12th power here. And so we're doing the 2000th power. Let's write 2000 as it's some multiple of 12 plus a remainder. So in other words, let's divide the 2000 by 12 and just get the remainder. Well, what is 2000 divided by 12? I think I wrote it over here. It's 12 times 166. We don't care about that 166, actually. The thing we really care about is that remainder. Okay. So in other words, that 8 is, what is it? It's just 2000 mod 12. Okay, what are we going to do with this information? We're going to rewrite that 2000 up here as 12 times something plus whatever the remainder is. But this is using properties of exponents. It's actually, we're going to use two properties of exponents. So we're going to use that one. And then we're going to use, let's say, this one. I have 12 times 166 in the exponent. That's the same as 7 to the 12, then to the power of 166. And what's going to happen here? So this is all happening, what? Modulo 13. That's our problem. Modulo 13. 7 to the 12 is 1 modulo 13. I'm going to replace it with 1. Okay? 1 to the 166 is 1. So our problem just becomes 7 to the 8. That's all we have to do. 7 to the 2000 and 7 to the 8 are going to be the same. Modulo 13. And how do you do 7 to the 8? Well, let's go ahead and try to figure that out. So it's the same as 49 to the 4. 49 to the 4. 7 squared to the 4, right? But this is, we can always replace 49 with anything that's congruent to mod 13. So 39 is a multiple of 13, so this is 10 to the 4. 10 squared is 100, so you have 100 squared. Okay, what is that? That's, I remember that 91 is a multiple of 13. Sort of a famous one. Number that looks prime but is not. So I notice 100 is 9 modulo 13. So it's 9 more than 91. And this is going to be 81. But that is congruent to 3 modulo 13. 78 is multiple 13. And that's our answer. 3 over there. So amazingly, we did this calculation completely by hand, and none of it was even that difficult, right? So we can always replace things with smaller numbers when we're working modulo 13. The main idea was turning that exponent into a smaller exponent, a much smaller exponent, and we were able to do that by noticing that every 12 powers are going to loop back. So every 12th power is going to be a 1, so I write the 2000 as 12 times something plus something else. Use exponent properties to sort of split off that something else, and this part's just going to be a 1. So typical example of Fermat's theorem. Here's another way you can use Fermat's theorem. And then I promise you we will look at why this is true. We'll look at a proof. Fermat's theorem. So remember when we did modular inverses? Fermat's theorem, we didn't really have a formula for modular inverses. We had a process for computing a modular inverse. Maybe I'll remind you what that is. But Fermat's theorem is actually going to give a formula. So Fermat's theorem gives a formula. It gives formulas for other things too, but it gives a formula for modular inverses. Mod P. Okay. It's only if P is a prime. Although if P is not a prime, there's still a formula, and it's going to involve Euler's theorem. Euler's theorem is essentially the generalization of this theorem when P is not prime. But when P is a prime, let me remind you what a modular inverse is, first of all. So modular inverse is a solution to... the modular inverse of A is the solution to this. AX is congruent to 1 mod P. It's a thing you have to multiply by A to get 1, something congruent to 1. So this is denoted A negative 1. That's the modular inverse of A. Let's write it down for Fermat's theorem. So it's A to the P minus 1 is congruent to 1. And can you see that you can actually use this to figure out what A inverse is. It's as simple as splitting off one of this is A to a large power, right? Just split off one of those A's, and you get A times A to the P minus 2, right? I split off one of them. Well, doesn't that mean that this thing right here is A inverse? Right? Because it's a solution to AX is congruent to 1, modulo P. So the formula for the modular inverse of A is that number right there, A to the P minus 2. So very useful. You just tell a computer to do this, and it can do it very quickly. There are many more uses of this theorem. We'll maybe explore one or two later, but as I promised, I'd like to show you one possible proof of this theorem. None of the proofs are too easy. They all involve at least one fancy idea, or rather creative idea. So it's no surprise that this theorem didn't come till the time of Fermat. But here's a one possible proof of Fermat's theorem. I'm going to show you one that uses a lot of what we've talked about, actually. Okay, so here's what we're going to do. We're going to consider a set, call it S, of just all the numbers 1, 2, 3, all the way up to P. Well, okay, up to P minus 1. Modulo P. So we're going to consider these as elements of Z mod PZ. Okay. So these are all the elements of Z mod PZ except for 0. Notice I'm not including 0 in this set. Starting at 1, going up to P minus 1. And now I'm going to take one element of this set. So for some element of this set, I'm going to construct a new set. I'm going to multiply every element of this set by A. And I get a new set. What is that going to be? It's going to be A, 2A, 3A, all the way up to P minus 1A. And again, I'm going to consider these as elements of Z mod PZ. Okay. I will give you an example. Let's take Z mod 7Z, so P equals 7. And we have the elements 1, 2, 3, 4, 5, 6. That's my set S. We'll take some element of S, let's take 3, and we'll multiply everything by 3. 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, but we're considering things modulo 7, so that's just 2. It's the same as that 2 there, right? 4 times 3 is 12, which is 5 mod 7. 5 times 3 is 15, which is 1 mod 7. And 6 times 3 is 18, which is 4 mod 7. So do you notice anything here? Well, I get all the same elements. They're mixed up, of course, but like the 3 is there, the 2 goes there. But I get some permutation of my set S. Okay, so it's the same set. It's just things are reordered. Okay, there's a set there the same. Here's what I want to claim. Both sets are the same. Have the same elements. Like when we talk about set in mathematics, we don't really care about the ordering. So really, I'm saying both sets are equal. Both sets are the same. Okay, so this is going to happen in general. However, we need to be careful because of this. What if I take something that's not a prime? So I'll take 6 be my modulus. I'll take 1, 2, 3, 4, 5. Let's multiply by 3 again. Look what happens. 1 times 3 is 3. 2 times 3 is 0 mod 6, right? 3 times 3 is 3 mod 6. So both 1 and 3 are going to the 3. 2 is going to 0. 4 times 3 is 0 mod 6. And 5 times 3 is 15, which is 3 mod 6. So this does not happen in general. We're going to try to prove this so that these two sets are actually the same. And this example is actually showing us that it's going to be a bit subtle. And we'll probably rely on primality, 7 being prime. That's the claim. It's the same sets. Both these have the same elements. That's what it means to be the same set. So first part of the claim, we don't get anything else. We don't get anything new. Here we got a 0, see? But we don't get a 0 there. We don't get anything else. What do we mean by anything else? Well, the only thing that's missing here is 0, right? So i.e. 0. How do we see that? Well, let's say I had an element of S. I'm multiplying it by another element of S. I'll just call these A and B. And suppose, for sake of contradiction, that we do get a 0 in our new set. So suppose, for sake of contradiction, we multiply together two things in S and we do get a 0. So these are both in S. Well, this cannot happen. That's what we want to conclude. And the reason for that is, well, what is this saying? It's saying that A times B is a multiple of P, right? 0 mod P. That means it's a multiple of P. So that means P divides AB. The product A times B. However, if P divides a product, that means that P has to divide one part of the product. Do you remember what that is called? That is called Euclid's lemma. And this was a very non-trivial statement in about numbers. The proof of this relied on the Euclidean algorithm, essentially, and the fact that we can write the GCD as a linear combination of the two numbers. So this is not an easy proof, but this is a true statement. If a prime divides a product, the prime has to divide one or the other piece. Okay? Translating this back into modular arithmetic, this means A is congruent to 0, or B is congruent to 0 mod P. That's a contradiction, because 0 is not in our S. 0 is not in our set S. Okay? So, claim 1 is done. We don't get anything else. Claim 2. What else can go wrong? This can go wrong. We can have multiple numbers going to the same number. Okay? That doesn't happen here. So our claim is going to be that all the elements in the second set, all elements here, A, 2A, 3A, all the way up to P minus 1A, are distinct. They're all different. And why is that? Well, let's suppose two of them are the same. Suppose I'm multiplying by A, so suppose like KA is congruent to LA modulo P. Okay. What are K and L? Or any two elements in my set. Suppose when we multiply them by A, we actually end up with the same thing. Well, what can I do here? I can translate this into a statement about numbers as well, but there's an even easier way to do this about integers. Let's just move the LA to the other side. So it's congruent to 0 mod P. And factor out the A. So A times K minus L is congruent to 0 mod P. this feels awfully similar to what we did here, right? Okay, so we have a product congruent to 0 mod p. That means, by Euclid's lemma, that A is congruent to 0. Okay, so this means that A is congruent to 0, which we know it's not, because A is an element of S. Or K minus L is congruent to 0. Right? That second one is possible, so this first one's not possible. It is possible that K can be congruent to L mod 0. Or, sorry, mod P. But what does that mean? This is a complete class of these are all the congruence classes modulo P. Right? There's one element from every congruence class, except for 0, I should say. If K is congruent to L mod P, that means that K and L are the same number to start with. Right? So it's not a contradiction, but it means that K and L are the same number. So if we had assumed that K and L are different to start with, then we have to get two different things. Right? Because the only way we can end up with the same number here is if we started with the same number here. So that is the proof that these two sets are equal. We haven't proved Fermat's theorem next, but we're going to right now with a really cool idea. Here's the idea. So we're going to consider these two products. 1 times 2 times 3 times, it's going to take everything up to p minus 1. Multiply them together. So in other words, p minus 1 factorial. But this is all mod p. And I'm going to take another set. I'm going to do a times 2a times 3a. Times all the way up to p minus 1a. What can we conclude about these two products? Well, they actually have to be equal, right? So they have to be congruent. They have to be equal as elements to z mod pz. So they have to be congruent mod p. These are the same elements as these, possibly in a different order, right? That's what we proved above. But it's all the same elements. You get one of each. And we're taking a product. Products don't care about orders, right? Everything's there on both sides. So these are the same. Let's rewrite this side over here as 1 times 2 times 3. I'm taking out all of these numbers. And I have a bunch of a's. How many a's do I have? Well, p minus 1 of them. So a to the p minus 1 power. Here's what I want to do. I want to cancel that and that. If I cancel that, I get 1 is congruent to a to the p minus 1 mod p. So we've proven Fermat's theorem. However, we have to be careful when we cancel things, because remember, modular arithmetic, you're not allowed to divide always. When are you definitely allowed to divide? I'm definitely allowed to divide if this is invertible. Right? If it's invertible, I can multiply both sides by the inverse of this number. So this, what I just did is correct, but it's only because this number is invertible mod p. Is invertible mod p. Okay. So what I technically did to cancel it out is I multiply both sides by the inverse of this number. By the way, how do I conclude this is invertible? You'll recall that the invertible elements are the ones that are co-prime to the modulus in general. And so for a prime, it's just anything that's co-prime to p. And these numbers are all less than p. There are definitely no factors of p here. Excellent. Okay, so that's Euclid's, sorry, not Euclid's. We use Euclid in the proof, but this is Fermat's theorem. Okay. And before we move on to the more general version, let me just give one more example of how you might use this. In fact, let's prove a statement about integers. So let's prove that any prime, actually not any prime greater than 2, so any odd prime divides some number of a very specific form. Some number of the form 1 less than the power of 2 to the n minus 1. Okay. Just for fun, let's look at a few examples. So, yeah, let's look at a few more. So, I'm gonna make a table here. Let's take this will be n. This will be 2n minus 1, and let's look at all the prime factors. So prime divisors. All right, n could be 1, 2, 3, 4, 5, etc. 6, 7, 8. I don't know how high I want to go here. 2 to the n minus 1. That's 1, and then 3, 7, 15. 2 to the 5 minus 1 is 31, 63, 127. These are called Mersenne numbers sometimes. They're not Mersenne primes. It's only a Mersenne prime if this ends up being prime, but in general, for general n, it's called a Mersenne number. Not 225, I'm sorry, 255. It's 256 minus 1. 255. 511, 1023. Maybe I won't do all of these, but okay. We have 3, 7, 15 is 3 times 5. 31 is prime. 63 is what? 3 squared times 7. 127 is prime. 255 is 3 times 5 times 17. 511 is actually 7 times 73. So there's a 73 showing up. And this one is 3 times 11 times 31, etc. And the claim is every single prime number greater than 2 is going to appear somewhere in this column. Okay, even though these numbers are getting very large very quick. I'm never going to miss any prime. Okay. The proof of this is basically just to immediately apply Fermat's theorem, and then it gives us the answer immediately. So what do I mean by that? So first of all, can we convert this to modular arithmetic? Well, let's take a prime. So let's say P is a prime, any prime. What do I want to prove? So I want to show 2 to the n minus 1 is congruent to 0 mod p, right? P is the thing that's a divisor, so that's the thing I want to be my modulus. Okay, and to be congruent to 0 means it divides p. Okay, that's the same as 2 to the n is congruent to 1 mod p. So I want to show that this is true for some n. Is there n that makes this work? Yes. You just take n to be p minus 1. Fermat's theorem. Okay, there's Fermat's theorem. It tells us that if we raise any number, in our case it's 2, but that could have been anything. Anything that's not a multiple of p. I raise it to p minus 1 power, I get 1. Okay. So for example, if I want to find one that has a 5, I just do 2 to the 4 minus 1. That's going to be this one, and I get a factor of 5. And notice I can do 2 to the 8 minus 1, because 2 to the 8 is still congruent to 1 mod p, right? They repeat every 4. I also get a 5, so I actually get infinitely many that have a factor of 5. If I want one that's divisible by 7, I just do 2 to the 6 minus 1, which is 63, and that has a factor of 7. Now, you might notice, that's not the first time we got a 7. We actually got a 7 earlier, right? We got a 7 all the way up there. And that's because, so we can look back at our chart here. It's because when we're modulo 7, there's some numbers that actually get to 1 sooner than the 6th power. For example, if I start with 2 and take powers, it would actually get to the 1 here. I only have to do the 3rd power. I don't have to go to the 6th power. The 6th power is guaranteed to be 1, but I might actually get something congruent to 1 earlier. Okay. So Fermat's theorem is not saying that the first time I'm ever going to get 1 is the p minus 1 power. I might get 1 before for some smaller power. However, this power will always guarantee that I will get something congruent to 1 for any a. Okay. Let's take this a step further. So there is a generalization called Euler's theorem. And Euler's theorem is essentially an attempt to make Fermat's theorem work for a non-prime modulus, for example, 10. However, that's hopeless, right? We cannot always, we will not always be able to find a power that's congruent to 1. In other words, there's no column here that's just going to be all 1s. However, we can do pretty well. So notice that this 4th column here does have a lot of 1s. It has a 1 for 1, 3, 7, and 9. Those are exactly the elements that are coprime to the modulus. Those are the elements that are coprime to 10. Okay? So we're only going to take those elements. So if A is coprime to the modulus, this is going to be the setup for Euler's theorem. M is our modulus. So we're going to take an element that's coprime to the modulus. Then, here's the conclusion. Let's see if we can figure out the conclusion, actually. So if we look back at this chart, if we go to the 4th power, okay, all of the elements, all of the 4 elements that are coprime to 10 end up becoming 1. And the 8th power repeats. Okay. What is the significance of 4? Well, 4 is exactly how many elements we have here that are coprime to 10. Okay. Anything else, like 2, there is no hope for ever getting a 1 here. And the reason is, if we did get a 1, then we would have some power of 2 and 10 differing by, we would have some power of 2 and 1 differing by 10. That's not possible. Okay, because anything that's a combination of 2 and 10 is going to be a multiple of 2. So 1, 3, 7, 9 are the only elements we can hope to ever get a 1. And in fact, we do get a 1, starting at the 4th power and then the 8th power. So what is that for? Well, in general, I'm going to call that, so a to the, what do I want to say? I want to say the number of coprime elements. The number of elements in Z mod M Z that are coprime to the modulus. I'm going to call that phi of M. So I'm going to immediately define phi. But the conclusion is that we're going to get a 1. Okay? No matter what A is, it just has to be coprime to the modulus. So, okay, where phi of n, phi of m is the number of elements among 1, 2, 3, etc., all the way up to m minus 1 that are coprime, that are relatively prime to m. Okay? For example, phi of 10 is 4. How am I getting 4? I'm just counting the coprime elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 is coprime to 10. 2 is not. 3 is. 4 is not. 5 is not. Shares factor of 5. 6 is not. Shares factor of 2. 7 is. 8 is not. 9 is. 9 is not prime, but it is coprime to 10 because it doesn't share any factors in common with 10. So that's how I got the 4. I counted those. This phi of m turns out to be the magical exponent for any modulus. Okay. So you're going to get 1, as long as you start with something coprime. The proof of this is exactly the same. So the proof is exactly the same as the proof for Fermat's theorem. It's just we need to be a little more careful with a couple things, but it's basically, I would even suggest you pause the video and try it on your own at any point in what I'm about to do. But I'll go through this relatively quickly, again, just because it's the same exact format. So what's the set I'm going to start with? I'm not going to start with everything. I'm just going to start with the coprime things. So A1, A2, all the way up to e to the phi of m, right? That's that's the number of coprime things. So this is, let this be elements, a set of elements, coprime to m in Z mod MZ. Okay. Remember what we did with Fermat? Proof of Fermat's theorem? We took any arbitrary element, and that's the thing that's ultimately going to end up being this A. So take A. This will be called S. So take A and S and consider the following. I'm going to consider the new set obtained by multiplying every one of these elements by A. Just like before. Only in this case, we have phi of m elements. Let's try it with this. Let's take 1379. So, yeah. 1379 would be our set in the case of 10. And we'll multiply everything by 3. We have to multiply it by something that's also coprime to 10. Okay, so our A, that's going to be our A here. And we get 3, 9, 7 times 3 is 21. That's 1 mod 10. 9 times 3 is 27. So see, the same thing's happening. We actually do get a permutation as long as we just stick to things that are coprime to 10. So that's the key in this generalization. The way to generalize Fermat's theorem is to just stay with elements that are coprime to the modulus. Okay, we'll consider this set. And again, the claim is these are the same set. These two sets are the same. These two sets are the same. Why is that? Well, again, there are two parts. Okay. The first part is actually a little bit more complicated than the previous one. So the first part, what do we had before actually? So we had, we didn't get anything else. That's our first claim. We don't get anything else. Anything else? i.e., in this case, it's not just 0 that we have to worry about. We have to worry about something not coprime to the modulus. So we want to show here that if we take something in S, multiply it by A, so I'll call maybe B my element in S, and I'll multiply it by that A, we want to show that we don't get something that shares a common factor with the modulus. So let's suppose we do get something. This was our strategy last time. Suppose we get something called C. So let's say one of these does share a factor with the modulus. So say that some prime p divides c and p divides m. Okay. Well, what does this congruent say? It says that AB minus C is a multiple of M. But if P divides C and M, it has to divide A and B as well. So P has to divide, sorry, not A and B, it has to divide the product AB, but by Euclid's lemma again, it has to divide A or B. So, or P has to divide B. Again, point out this is Euclid's lemma. What does that mean? It means that A and B were not coprime with M to start with, right? But we took them from S. So that's our contradiction. We took these from S. So that shows we can't get anything else. What's the second thing we want to show? Again, this proof is really exactly the same structure as what we did before. So the second part is it's just more general. Like the arguments involve a little bit extra. So the second part is, what do we want to show? We want to show, let me grab a page from before. Where is it? Here we go. Everything is distinct, right? All the elements from my new set are distinct. We don't get 2 3s down here, for example. So all elements, we're starting with distinct elements. All elements in my second set are also distinct. And that would prove that it's just the exact same set as the original one because both sets have the same size. Okay, so all of these are distinct. Why is that true? Well, let's suppose we get 2 of these ending up being the same. Modular M. What does that mean? That means A times AI minus AGA is congruent to 0. Factor out the A, moved it over. But what do we know? We know that A and M are coprime. We don't know about this thing here. Like, we know each of these separately is coprime, but we don't know about the difference. But since A and M are coprime, sorry, not A and B. Where is it B coming from? A and M. Since A and M are coprime, what do we conclude? We actually can conclude that M is going to divide this number here. So why is that? So in other words, this is congruent to 0 mod M. Why is this? This is the slightly more general version of Euclid's lemma that I think we saw once before. So this is if we have a product congruent to 0 mod M, and we know that one of the parts of the product is congruent to coprime with M. For example, A. Then actually the second part of the product has to be congruent to 0 mod M. So why is this? Well, it's essentially the same idea as the proof of Euclid's lemma. I think I showed this once before, but it's such a nice idea. I just can't resist showing it again. So what's the idea? The idea is to use the GCD condition to write 1 as a linear combination of A and M. Sorry, I'm kind of running out of space here, but I actually won't need much space. And then the idea is, it's this nice idea, you multiply it all by B. And then what do we conclude? Well, we know m is going to divide this. M is certainly dividing that. That concludes m divides b. So in other words, b is congruent to 0 mod m. Okay. So we're seeing this idea again. That's the second claim. So we've proven our two claims. The next part is the fun part. It's you take all of these elements. You take all of our original elements. So you consider the product of all my original elements. We're taking a product over all of them. And that's going to be congruent to the product of all my new elements. The same ones multiplied by m. They might be reordered, but they're going to be all the same elements. So the products are actually the same. And we rewrite this. Again, this is really, I'm just doing the exact same thing as before. It's just there's a little more work to justify a few things. What power of a do we have here? We have the phi to the m power. Okay. And so we conclude, because we can take the inverse of this, the product of two invertible things is again going to be invertible. It's actually the same argument here if you think about it. But we're going to get 1 is congruent to a to the phi of m, because we can multiply by the inverse of this thing. Mod m. Great, so that is Euler's theorem. Slightly fancier version of Fermat's theorem that works for any modulus. Okay, you just have to compute this phi of m. So let's do an example of this, and then we'll conclude the lecture. So let's do 7 to the power of 2000. Instead of mod 13, let's do mod 100. So we want the last 2 digits. That's what mod 100 means. Can't use Fermat's theorem. Okay. So don't assume that 7 to the 99 is going to be congruent to 1. Mod 100. Not necessarily true. That only works for the modulus this prime, that you go 1 less. Instead, our magic exponent is going to be phi of 100. Okay, if our modulus is composite, we need to compute phi of 100. What is phi of 100? Well, we want to count all the numbers from 1 up to 99 that are relatively prime to 100. And there are multiple ways to do this, but here's what I'll do. I will count the numbers. So 100 is 2 squared times 5 squared. I'm going to get rid of all the multiples of 2. So there are 50 multiples of 2. So the multiples of 2, I'm counting them. 50 multiples of 2. Sorry, so I'm going to take 100 numbers first. There are 100 numbers, 1 up to 99. I'm going to take away 50. Actually, there are 100 numbers from 0 up to 99. There are 50 multiples of 2, including the 0. There are, how many multiples of 5? There are 20 multiples of 5. Right? As 100 divided by 5 is 20, so including the 0. Is this the final answer? Because I've already subtracted out the multiples of 4, right? I've already subtracted out the multiples of 5 and 5 squared even, right? 25, those are included in there. Well, this is actually not the final answer, and that's because there are certain numbers such as 10. 10 is a multiple of 2 and 5. I subtracted it out twice. I was counting that in my 100 initial numbers, or 100 numbers here. I subtracted out the 10 twice. It's part of multiples of 2 and the multiples of 5. I want to add it back in. I only want to subtract it once, in other words. Right? So I'm going to add back in the multiples of 10. And then this is going to do it. There are 10 multiples of 10. Okay. So what is this actually? It's 100 minus 50 minus 20 is 30 plus 10 is 40. I think we counted this right. We don't need to do anything else now. In general, this is a rather difficult process to compute this function. We're going to see actually better ways to do it. But phi of 100 is indeed 40. So that is the magic exponent. How do we use that? Well, we use what Euler's theorem tells us. Euler's theorem tells us 7 to the 40 is congruent to 1 mod p. Not mod p, sorry, mod 100. We want to do 7 to the 2000. So we have to figure out how many 40s go into 2000 and what our remainder is going to be. We don't get a remainder, do we? Right, 2000 is just going to be 50 times 40 plus no remainder. So 7 to the 2000 is 7 to the 50 times 40, which is 7 to the 40 to the 50, which is 1 to the 50, which is 1. Okay. Mod 100. It's 1 mod 100. That means the last two digits of this are going to be 0, 1. Right? It's 1 mod 100. So these are the last two digits of 7 to the 2000. Notice if we wanted to do 7 to the 2023 instead, for example, we would do the same thing. We'd write 2023 as, well, still 50 times 40, but this time there's a remainder. So we're going to get we still want to divide by 40, right? Because that's when our pattern repeats, right? So that's how we turn a big exponent into a smaller one. That's going to be 7 to the 40 to the 50 times 7 to the 23. And this is going to be 1, so we're just going to get 7 to the 23 mod 100, whatever that is. Okay, so that is Euler's theorem. You can use it whenever we have any modulus at all, as long as that 7 is coprime to 100. Okay, if we were trying to compute 8 to the 2000, then we wouldn't be able to do it with Euler's theorem. I also just want you to note Fermat is a special case of Euler. Why is that? What does Euler's theorem tell us? If we have a prime modulus, well, the magic exponent is going to be phi of p, that prime modulus. How many numbers between 1, 2, 3 up to p minus 1 are coprime with p? It's everything. Right, so 1, 2, not 0, but 1, 2, 3, 4, 5, all the way up to p minus 1. That's p minus 1 numbers. Okay, so you just get Fermat's theorem from Euler's theorem. Euler's theorem is the more general one. Okay, that's it for this lecture. Thanks for watching.